Okay, good afternoon, everyone. Welcome to the second part of this Lunch and Learn series on building a modern data and analytics platform. My name is James Green. I'm the head of data analytics and AI at Ancoris. Right, okay. So last session, this is a three-part series. Part one, we covered all about ingesting your data, storing it into Google BigQuery, so their hyperscale data warehouse. And then we looked at how you transform that data using DBT, Data Build Tool. If you didn't catch that one, you can go and watch it, stream it. It's on our website. Session today, we're going to be looking at everything ML. So we're going to be covering what it means to identify some of these AI-driven insights. And then we're going to look at how what the process looks like. And we're going to be looking at some case studies that we've done as a consultancy. We're also going to be kind of delving into some of the technologies that are available through Google. And sometime next week, we're going to do the last part, which is all about Looker. So it's all about visualizing this data. So once you've got these insights, how do you get them in a timely fashion to people that need them? How do you engage business leaders? And how do you embed this stuff in all of your systems, whether it's web or mobile apps? So yeah, it'd be great if you could join us for that next week. Okay, so this is our reference architecture that we use for building modern data analytics platforms. We covered this in the first session, which is highlighted in the pink square here. So we were looking at ingesting everything from these different types of system on the left into BigQuery here, and we're using DBT to do transformation. So we kind of covered this. If you didn't, as I say, if you weren't on that, please go and watch that if you think that would be kind of beneficial. In terms of what we're covering on this session, we're looking at this slice. So we're looking at everything kind of ML and AI based, and we'll be covering some of these technologies, including BigQuery ML, Cloud AutoML. We'll be looking at AI platform, and we'll briefly kind of touch on TensorFlow. And then next week's session, we'll be covering the kind of the final slice, which is making this stuff available to action. Right, so we're going to start off. We're always conscious with these sessions that there's going to be a spread of people. Some of you will, know the terminology, know what ML looks like, live and breathe it. Others, won't. So I think it's useful. We're going to do a quick session, just a refresher really on looking at an example ML workflow. And I'm going to pick a simple classification problem. And the problem is we want to know if we can play cricket tomorrow. And some of the factors that the factors that we're using for this example are basically the weather. So we've got some weather information there, you can see in the first four columns. And then finally on the right, whether or not we can play cricket. Okay, and the idea is here that we're going to build a classification model that if you feed in some weather data, it'll predict if you can play cricket or not. So imagine if we had this as a weather forecast for tomorrow, can we play cricket? Now, in terms of some terminology, so we call play yes or no in this example, we call that a target variable or on the y-axis. And then these, in this case, temperature are called features. And you'll hear this terminology around feature engineering. All that really means is making these features available. So if I had to do some calculations to, say, derive that temperature, then that would be described as feature engineering. Now, features come in many different forms, but the most popular two are a continuous, and that basically means a number. So like in this example here, you've got humidity. Another continuous feature example would be temperature. And then the other common one that we come across is categorical. So an example here is outlook, sunny, overcast, or rainy. Also windy, that true and false, that's also categorical. Now, when we actually train a model, essentially what we're using is historical observations. So one of the first questions that we have if we're looking at a potential ML use case is there training data available? Are there historical observations? So if we take this cricket example, if we didn't have any information like this that said particular outlook, temperature, etc., enabled play or not, we basically couldn't train a model. There's nothing to train it on. Now, when we look at historical observations like this or training data, the thing we're trying to predict, in this case, play yes or no, is known as a label. So you'll hear this often. People will say things like, I need a labeled data set, or they'll say, for example, I need to go and I've got some images, I want to know which ones are cats, so I need to go and maybe outsource to people to go and label those images as cats. So when they're talking about labeling, that's what they're kind of alluding to. On historical observations, a few tips and pitfalls just to watch out for. So as a general approach, the more observations you have, the more accurate your model will be. Now that's diminishing returns. So if you had, 10 lines of training data, you're not going to get a very accurate model. If you had 1 million versus 100 million, you're going to get a kind of diminishing returns on the accuracy of that model between that million and 100 million. So be kind of mindful of that. Number two is really important. So your model is only as accurate as your observations. Now, for our cricket example, the observations are going to be accurate, I'd have thought. I would have thought we could get information on was the game able to play or not, and what was the weather like, right? That's going to be quite easy or accurate. Some other ML models, it's not as simple as that. And often what we're actually doing is the observations we're actually computing. So if I give you an example of a recommendation engine, which we'll cover a bit later in the session, if you think about something like Netflix is predicting what you're going to watch next based on what you found highly engaging. Now, you're not explicitly telling Netflix if you're engaged with something. So the team at Netflix are having to, to feature engineer those observations, and there's going to be some kind of calculation, whether it's, how long are you watching the movie for? Did you just fall asleep, or were you really watching it, etc. So it's worth keeping that in mind. And the final piece, which is probably but this is also very important, is to avoid what we call imbalance in your observations. And I'll give you an example of what that means. So imagine this is what we call an imbalanced training set. So imagine, I've simplified this, but imagine that the training data that we fed into this model was 99% play went ahead. Okay, so in this example, we've only got one example at the bottom here when play was cancelled. And you have to be very careful here, because if you think about this from a machine learning standpoint, it can get a very high accuracy if it just predicted that play would take place, because in 99 cases out of 100, it's going to get that right. So you have to be very careful with imbalance. So if you've got any kind of machine learning problem, when you're thinking about what data you've got available, always try and think about the balance. So you want to, in this case, you want a nice spread of play yes, play no, with a good spread of different outlooks, temperatures, humidity, etc. Now, when you're training these models, you'll hear this, people talk about training sets. So what that means is, say this is all the data we've got to work with. When we train our model, we first split that into a training set. Now, typically we take 80% of the data. So I'll carve out those rows there, and I'll use that to actually train the model. The model will then learn off those, and then we have what we call a test set. So typically this is the remaining 20%. And we feed those into the model once it's trained on that training set. And then, because we know the answer here, we know, yes, yes, no, we can feed into the model these inputs and just verify. If the model says yes, 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 then we know that it's not. We can get an accuracy score, and that's what you're ultimately aiming for in that training kind of exercise. Now, so again, some of the few pitfalls that we see. We've talked about imbalanced training data. Another thing you'll hear about is overfitting. Now, overfitting basically means when a model performs really well on a training set, but really poorly on unseen examples. So And this is a real gotcha. It's very often you'll get a machine learning model on some training data that's maybe 80, 90% accurate, and you think, wow, smash this, this is going to be phenomenal. And then you put it out in the field and you start putting real predictions through it, and suddenly your model accuracy just completely plummets. And often that's due to overfitting. And we've got a bit of which is actually a real life example, not something that we worked on, but this is so the challenge here was a company was asked to basically build an image classification model that would take an image and it would say if the image is an image of a wolf or not. Okay, so is this a wolf? So you can imagine that you would, in order to train this, you would have lots of images, some containing wolves, some not. But you're basically trying to train the model on what a picture of a wolf looks like, what a wolf looks like. And here's some kind of images that the company were kind of feeding into that model, which seems sensible, doesn't it? They're all wolves. Right. So we're going to do a quick poll here. So this is the humans, I guess. So let's see how the humans do. So I'm going to ask the question, do you think this is a wolf or not? It's no trick question. Just, is it a wolf? Yes or no? Let's see how good people are at identifying wolves compared to how the AI model did.
Right. 90% of the people say it is not a wolf.
Okay, well done. That's right. So it's exactly right. So it's not a wolf. It's actually a husky. Okay. So humans did really well there.
Did you get that, James?
I did get that. Yeah, I heard that. So 90%. Yeah. So the humans did well there. So yes. So humans got that correct. And we know that. Imagine how we're processing that information. All the different, the eye color, the shapes, etc. And we come to that conclusion based on our intelligence that it's a husky. Now the AI model, interestingly, if you were to feed this image into that AI model that they trained, flagged it as a wolf. Okay, so it didn't get it right, which is 1 to the humans, 0 to AI. And the reason for that was basically overfitting. And what the problem that they had when they trained this model is all the images that they fed in, 99% of them contain snow, or a snow in a combination of trees. So what the model was actually looking for, so in this image, the model looks at this and says, yeah, I can see loads of snow in there. So based on what you told me in the training set, this is statistically likely to be a wolf. So it wasn't looking at anything to do with the actual animal in the picture. And even there were images that you could, is this, I didn't even bother with a poll, is this a wolf? Well, clearly it's just trees, silly, okay, ridiculous. AI model, yes, it's a wolf, because again, it's looking at snow, it's looking at snow-covered trees, pine trees, etc., where wolves live. Yes, so it's highly likely there's going to be a wolf in the picture. So yeah, you have to be really careful with overfitting. As I say, it's a real-life example, but there are many others. And if we think about, okay, is it a wolf or not? Perhaps the implications of getting it wrong aren't too serious. But when you're looking at things like diagnosing cancer, self-driving cars, is the road ahead clear? Yes or no? It obviously, it's very, very important to make sure that you don't overfit your model. Okay. So the basic premise is once you've trained your model, you are then going to move on to evaluating it. And what this basically means is feed the model using unseen observations to measure its accuracy. So in that prior example, this would be an example. We'd throw some of these in to try and basically fox the model and see how it performs. And then at a high level, what you're then doing as a data scientist is you're repeating this process. You're training, tuning, which means tweaking hyperparameters, which we'll kind of touch on a bit later, and then you're evaluating it. And you repeat this process until you get a model that is of sufficient accuracy, sufficient kind of performance to train it, etc. But that's the high-level kind of process. Once you've got your model, you then got to think about actually productionizing it. And I guess how we look at this is you want to build that training pipeline into your kind of data, your data analytics platform. So, for our example, the cricket scores, we'd need to ingest that weather information. We need to do probably some kind of transformations in DBT, some kind of feature engineering, and then we'd need to build an ML pipeline that trains that model. Maybe we train it on a weekly basis, maybe it's a monthly basis, depending on how we think that model may vary. And then the second part to it is kind of, actually doing our prediction. So if we look at this, again, trivial example, but once I've got my cricket model, I want to feed it these features, and I want the model to tell me tomorrow if we can play cricket or not. And we talk about a prediction pipeline for that. So again, we may have some kind of information, some kind of weather information coming in, and we're going to be pumping that into our model, and then we get an answer, and we may surface that answer, to whoever needs to know that information. All right, so now we're going to move on to some case studies. And before we do that, I think it's worth debunking some of these myths around machine learning. And we get asked this a lot. So some people think that, I guess, machine learning AI is a silver bullet or a magic wand, and will solve all your problems for you. That's far from the truth. Really, machine learning is only suitable for problems framed in a certain way, and in many cases, it's not applicable at all, or it's actually not performant compared to other options. And some of those options can be, very kind of trivial approaches. So ML can actually bring in more complexity. We see it as a bit of hype around it. People feel like they should be using it, and the answer is it is highly effective, but you have to have some understanding of your use case, and you have to have some understanding of your data that you've got available, and how accurate the end model is going to be. So the answer to that is yes, it is highly effective in certain situations. Now, in the last session, we covered Sigma Sports. It's a client we're working with at the moment. They are a premium cycling and multi-sport retailer. They've got a couple of big kind of experience-based stores in the UK, but most of their activity, their sales are online. And we talked through these slides. I won't cover these in too much detail, but basically we're building a modern data warehouse for them. So we're ingesting marketing data, clickstream, so where people are clicking on the website, all their sales data in a platform called VendorTan. Interestingly, all the customer interaction data, so if they receive a complaint or a question, that's coming into us through a system called Freshdesk. And then they've got some supply chain and pricing information in a platform called Borderfy. So we're ingesting that all into BigQuery. We've got an analytics layer in Data Studio, and in the future we think Looker, and then we're surfacing some insights. Now, they've got some really interesting machine learning use cases, and I'm going to delve into a couple of these, but the ones that they're really interested in are predicting customer acquisition, retention, and churn. They're looking at segmentation of customers by lifetime value. And this is one of the ones we're going to cover in a minute, but this is a predictive lifetime value, just to emphasize. So this is not saying how much has each customer spent today. This is about someone potentially browsing your site or making a couple of purchases and then saying, what do I think, how valuable do I think this customer is going to be to my organization? We've got some ML use cases around product buying and supply chain, cash flow optimization and forecasting, and an interesting one on customer support ticket intention classification. So they've got quite a broad mix. Okay, so the first one I wanted to just touch on is the ML use case for predicting LTV, so lifetime value. So if you imagine here, I've got two customers, say Bob at the top, Jane at the bottom. Now Bob, in his first kind of month's activity with Sigma, he buys some energy bars for £16, and Jane buys a quite an expensive bike, so £12,000 specialized bike. And in month 2, Bob buys some more energy bars. Jane buys a nice set of carbon wheels for £999. Month 3, no surprise, Bob's come back for more energy bars. Jane this time has gone for a really nice pair of shoes, 359. And this is what we're trying to get to in LTV. So one of the things that we're looking at is, if we had this information, we want to build a model that will predict what the lifetime value of that customer will be. So what is the next purchase? Is it going to be high or low? And how long do we think they're going to be a customer for? And how long, typically how much do we think they're going to spend over that period? And you can imagine with this kind of information, if you were to say market a pair of shoes, you should know from here, we know as humans that we'd want to market this to Jane, not necessarily Bob. So there's a lot of value in getting this. So if we've got another 2 users, so imagine their first purchase at the top there was energy bars and the bottom there was a bike. Who's going to be the more likely to be a high value customer? Now, based on what we've seen, we can make an assumption. Actually, it's the guy at the bottom there. But this is what's basically happening with our LTV model, and the information that we're feeding into it is a combination of some demographics about the person. We've got their activity in terms of what they've been buying. So we've got their sales. We've got things like how they got introduced to Sigma, what channel they came into. Did they go direct from, say, Google? Did they come from purchasing in store? Did they come from an Instagram ad? Did they buy with a discount, for example? These are all relevant. What time of year did they first make their purchase? And then in addition to that, we're also looking at these 3 key measures on the left, or features as we call them. One is recency. So when did they last order effectively? Frequency is how often are they ordering? So it's a way of looking at kind of measuring loyalty, really. And then the final one is a monetary value. So you can imagine that Bob's low monetary value in this case, and Jane is very high. And then the idea is that once we've trained this model, we can then segment these customers into low LTV, so band 1, and high LTV, band 10. And that's really useful for any retailer, because, for example, if you want to target your advertising, if your goal is to get high value customers and your LTV, your value is tied to revenue, then from this you can see which customers are going to likely to be those high value, and therefore you target your advertising at those customers. If you bias your model to actually look at something like loyalty, so the frequency of how often people are buying, you want people that are buying often, then again that can kind of control maybe certain decisions you're making, who to send offers to, for example. If I know that someone's frequently buying, I don't want to cannibalize my profit by sending them offers if I don't have to. So a really common and really highly effective use case in retail. And the second one this is really interesting. This is around product buying. So if you think about any retailer, they'll have a division that their sole responsibility is for deciding which products to buy, who to buy them from, when to buy them, and how many to buy. So there are a number of features, again, that feed into looking at a model like this, where you're looking at ultimately trying to predict what products that buyer should purchase and how many. So one of the things is product demand. And that's based on both product demand that's happened in the past, and also you can kind of predict which products we think are going to be purchased in the future. So you've got product demand. Then we've got availability. So if I'm a buyer and I know that this is a trivial example, but if there's a buyer and I know this are my 2 customers and I know this is what they're going to buy, then obviously I'm going to go and order 4 packs of energy bars, bike wheels, 2 pairs of shoes. Simple. But then what happens if the supplier only has 2 packs of energy bars and it only doesn't have that green pair of shoes? There's some kind of decision making there. Do I buy a different energy bar? Do I think actually the customer's not going to buy from us, they're going to buy somewhere else? Do I buy a blue set of shoes? It's those kind of decisions. So it's really important to know what products are available into this model, as well as what there's demand for. And the third element that affects buying in a typical retail is how much cash flow does the company have? How much cash does that buyer have in order to make purchases at that point in time? So to do this, you need to have an accurate view of how much cash flow you've got as a company on a daily basis. And then you have to start trying to model how you're going to spread that. So for example, I wouldn't necessarily want to buy 2 bikes like this and burn all my cash, because I'm going to lose out on that other customer. I'm probably better off to do a spread based on what I know. And we've developed a product called CFO Lab that's all around cash flow analysis. There's some predictive elements in there. So yeah, so in this use case, we're kind of tying that in to help with the cash flow piece. And like all good ML and AI, it tends to get more complicated the more you look into it. So there's actually more factors here that are feeding into this model. So warehouse space, for example. So a buyer can't just go and buy necessarily a ton of bikes, because they're going to quickly fill their warehouse space, and they can't exceed that warehouse space. So there's a warehouse as another variable, what future purchase orders have been placed, and then you've got things like seasonal demand. So yeah, so a really interesting use case. Okay, now for this next kind of section, we're going to touch more on the technology. So we've talked about some kind of use cases. We've given a bit of an intro into some of the essential kind of thoughts around ML, but now we're going to be looking at technology on Google Cloud. So this is a really good quote, I think, from Eric at MIT, and his view, and I actually agree with him, is this now is like the age of machine learning. And to summarize this statement, saying that there's been a number of general purpose technologies, and these are significant technologies that have changed, the kind of economies of the world. So we go back, we can look at things like steam engine, electricity, internal combustion engine. And in his view, the most important in our era right now is artificial intelligence, and particularly he calls out machine learning. And something that we look at as a company, so we think that Google have recognized the demand for accessible data science. So that is what Google, we think, have done a really good job at, is simplifying the process of applying data science without compromising its effectiveness. So that's really important. It's worth saying that again. They've simplified how to apply it without compromising its effectiveness. And recent innovations, and we'll talk through these products such as BigQuery ML and AutoML, really from our point of view, have turned this aspiration into reality. And we'll be touching on some of those in a minute. Okay, so we're going to start with BigQuery ML. So in the last session, we did some live demos of BigQuery, the Google's hyperscale warehouse. If you want to see that, we were querying kind of billion row tables and just showing how kind of quick it is. Yeah, I would recommend that you watch that if you've not seen it. But there's an extension to BigQuery, which is called BigQuery ML, so BigQuery Machine Learning. And what this essentially allows you to do is train a variety of different models, ML models, using SQL. So typically, and we'll touch on this in a minute, but typically what happens with data science is you have a team that very specialized, that can be quite siloed. They'll be using languages like Python and scikit-learn packages and all these kind of wacky ways that they have to try and productionize everything. It becomes really complicated, really kind of difficult. Whereas we really like BigQuery ML because most people who work with data, there's one thing they all know, and it's SQL. And I don't think that's changing. It's one of the first languages they learn, really. And so BigQuery ML allows you to basically train and predict models using basic SQL. So here's what it looks like as an example. So here I've got a model type called a boosted tree classifier. So I'm training a classification model here, and you essentially create some features in a table, select from that table. So you can see I'm doing a select star from my set of features, and then you create the model just like you create a table or review, really. So it couldn't be any more simple than that. And then the language where you run predictions is exactly the same. There's a model.predict once you've created that model, so you can interact with it as if it's like a table or a view. So really, really clever. And BigQuery ML, Google have been really good in terms of putting the main models that we think that you need to cover probably 90% of use cases. And I've picked out a few here. So a linear and logistic regression model for doing churn analysis. So if you want to predict, if you're a subscription-based company, think of like Gusto, HelloFresh. If I want to predict if someone's going to churn, they're going to stop buying from me, then I could use a linear and logistic regression model on BigQuery ML. Segmentation, so unsupervised learning using a model called K-means, and we'll give you a demo of that in a minute. Personalization, there's a model called matrix factorization, and again, we've got a case study on that. So you get the idea. So they've got a really good cover of models. And I think this slide's really good. So this is what typical data science looks like, or traditional, which is kind of crazy. It's not been around that long, but already there's this idea of traditional data science. And you're doing all of these different activities. So you're doing data engineering, sampling data, you're programming things like Python and Scala, you're trying to deploy it and productionize it. You're resource provisioning, so you're spinning up different compute engines, you're having to move data around, all these different activities. The actual value add is relatively small. So it's this kind of activity here. BigQuery ML, you don't have to do any of this other stuff. So you can spend your whole time actually extracting value. And the really nice thing that we like about it, so if you imagine, if I build a training pipeline, which I showed you using that create model statement, I can put that in so we use dbt to do all of our data transformations, so all of our pipelines. I can just stick that in a pipeline as if it was a table. It just happens to be a big machine learning model instead of a table. And same with the prediction pipelines. When it comes to serving predictions, again, I can just do everything within dbt. Don't have to learn any other languages or any other tools. So yeah, so we really, really like it from that standpoint. This is an example of clustering in BigQuery ML. So for those of you who don't know, clustering is what's called an unsupervised learning algorithm. And it's unsupervised because if you think back to the cricket example, we had a training set of data. So we're supervising the model, we're hand-holding it, and we're saying, look, here's some information to learn off. Go learn it, basically. With unsupervised, with clustering, what you say is, okay, say here, in this case, we're saying, here's a load of stations. These are from the cycle station scheme. That's, if you know, in the UK, the Boris Bike scheme, or the Santander cycle scheme as it's known. These are all the cycle stations. There's about 700. And in this example here, we use BigQuery ML, and we said, okay, based on the proximity from the City of London, go cluster these in 6 clusters. And that's effectively what this has done. You can see the clusters kind of with the proximity from the center. And this one was actually clustering by longitude and latitude. So we're taking them and we're saying, okay, just go and form 6 clusters, and the machine learning model will go and do this. It's really useful for things like customer segmentation. So if you've got customer data, recency, frequency, monetary value, have the machine learning decide what those clusters are, as opposed to what can be not as effective is where we use our own human knowledge and we try and cluster them. So that's clustering. This is an example with classification. So this is actually from our CFO Lab product, and this is upcoming payments from my customers. So when I'm looking at cash flow, I've sent some invoices out. And in days 8 to 14, so a week to 2 weeks, I've got about 200 grand coming in. So as a CFO, I think that's great. Everything's happy. I'm going to be able to pay everything off. But actually, in reality, it might be very different. And what we do is we use BigQuery ML to look at the payment compliance of that customer and customers that are similar to it, and then we come up with a prediction that predicts this is actually reality, is that 61,000 of that 200,000 is actually going to be late. So that's an example there of using BigQuery ML classification. And then finally on BigQuery ML, I wanted to touch on a case study just to show you how powerful it is really. So this is a project that we did last year, that we have a public case study on it if you want to go read it in more detail. But essentially, it was all around content personalization for a company called Play Sports Network. So PSN, as they're known, they're the world's largest cycling media company. They've got a number of YouTube channels. You'll probably recognize it as GCN, so Global Cycling Network. They've got 40 million, or that's actually more than that now, fans on YouTube. Now, they have a mobile app on the right-hand side, and one of their goals was to increase the usage, what they call stickiness, of their apps. They want more users to become engaged. They want more users to use it on like a daily basis. So what we did for them is we developed a recommendation engine, which is an element of machine learning that predicts how likely a user is to find a piece of content engaging. So if you imagine the home feed of all their content, a bit like if you're using LinkedIn or Instagram, you're serving up what you think that particular user is going to find engaging. So just like on LinkedIn, if I fire up LinkedIn and you fire up LinkedIn, we're going to see totally different content. So LinkedIn's got its own recommendation engine that's doing that. Now, they had a data science team in-house. They had some familiarity with GCP products. And I guess they tackled this using the traditional approach. So they'd use Python. They just didn't really get the results that they were hoping for. So they asked us to try and improve it. Now, recommendation engines, is worth noting, are a really challenging area of ML. So much so that Netflix offered $1 million in prize money to the data scientists who could produce the best recommendation engine to drive their what to watch next. So it's really big business and really important for companies like Netflix, like Amazon, recommending you what to buy. So they put a lot of work and emphasis into these models. Okay, now what we basically delivered for them, so we delivered what's called a matrix factorization model. That's available in BigQuery ML, so we used BigQuery ML to actually train the model. We did it all in SQL, we did it all productionized using dbt. Now, one of the things that was quite difficult is, if you remember, I talked about features, the accuracy of your features. So this was an example where we had to come up with an engagement score. So for every user and every bit of content, we had to kind of say, how engaged did that user find that content? And that's actually quite a hard problem in itself. So we had to do lots of clever analysis of the logs on the app. So how long did you have it on the screen? Did you zoom the image? Did you like it? Did you forward it? All those kind of things of what is scoring, so we can say, okay, what did this user think of this bit of content? And if we didn't get that right, like I mentioned before, accuracy of the model is only as good as the accuracy of that scoring mechanism. We also built a single customer view for them because they weren't really sure. User IDs were evolving. It was actually the same person, but it was difficult to track if it was the same person or not. So once we got the engagement score, single customer view, then finally we essentially used BigQuery ML to train this matrix factorization model. Yeah, so that's just highlighting what I was just saying for scoring user engagement. Recommendation engine is only good as its ratings. Training the model in terms of the GCP architecture, we essentially used our similar approach. So we had BigQuery ML where the model sat. We had dbt for all the pipelines. There were some complexities around billing, but you could probably look at, if you want to read our article or a case study on that, you can kind of learn more about that. And then it's worth just kind of talking around BigQuery and just how powerful it is, really. So when we train that matrix factorization model, you basically feed in all the users and all the content and all those scores, and it produces a matrix that you can say for a particular user, it will rank the content from most likely to engage to least likely to engage. Now, that model for them at the time was about 45 billion rows, so it's a big table that it outputs. And in terms of processing time on BigQuery, we talk about slot time. So a slot is a theoretical period amount of computation. So by default, you get 2,000 slots from BigQuery. And if you take a single slot, and when we talk about slot time, it's how many how long would it take on a single slot to process that? Now, with this particular problem, it was actually something like 53 days of slot time. So what that means is had we run that on a single slot on BigQuery, that would have taken 53 days to compute that matrix. So you can just get a feel for the complexity. Now with the hyperparallelization in BigQuery, I think we ran it on 500 slots. We brought that down to something like 2.5 hours. You could go and throw 10,000 slots at it if you wanted to, but for us, we're building this daily, so we felt that was okay. And there's a little bit here on how much that costs. And I always find these pretty amazing, these figures. So if we look at some of the feature, this is the feature engineering on BigQuery. So think about this is like running all the data pipelines for that model that are upstream. So that was processing 160 gig an hour. Cost about 80 cents per hour to run. So that's $16 daily. And then actually to train the model, so to do that 53 days of processing in about 2.5 hours it took, was ranged between $40 and $60. So the daily cost of the client for running that model was kind of tops $80, call it. And then they're paying nothing for BigQuery. If they don't use it, they don't pay anything. There's no infrastructure. So it's kind of phenomenal, really, when you think about the amount of compute access they have access to. Alrighty, so that's BigQuery ML. I'm now going to touch on AutoML. So AutoML is another Google product, and this is from the Google CEO. So I'll read this out. So today, designing neural nets is extremely time-intensive and requires expertise that limits its use to a small community of scientists and engineers. That's why we've created an approach called AutoML, showing that it's possible for neural nets to design neural nets. So that's effectively what AutoML does. So it actually uses AI to select and train machine learning models for you. Really easy to use. There's a UI that you can use, or there's an API that you use for both training and predicting. And it leverages more than 10 years of proprietary Google research technology. So if you think about Google, are arguably the world leader in AI. They've got a lot of models that are sitting behind the scenes. And AutoML, all the time, every time you train a model, it's helping other models learn about what's the most effective model to use. So yeah, really, really good technology. And it covers a suite of different applications, which is also really, really useful to know. So for example, if you wanted to do that, is it a wolf problem? Then there's AutoML vision. So you can do things like image classification. Is it a wolf? You could do object detection. So count how many wolves are in a picture based on images and labels. It can do video as well. There's a whole suite of products on natural language, and we'll talk a little bit. But we've actually got a use case on that in a little bit. And the final piece is structured data. So this is really looking at BigQuery data, and you can do things like regression, feed-forward deep neural networks, boosted decision trees. So yeah, it's really, really powerful in terms of what it offers. So here we've got an example here, AutoML vision, and then with some video intelligence here. So you can do things like object tracking, object identification. It has pre-built stuff as well. It even has things like celebrities. So it'll point out in your videos if there's a celebrity that features, and it can track the celebrity around. So there's loads of different plugins. AutoML, the natural language, we'll go into this in a bit more detail, but there's some really good products here. There's translation as well. So if you need to, do any kind of language translation or custom translation, there's models that will basically automatically train for you. And then AutoML tables is what we've kind of touched on. So that's what if you want to train something like a regression model, for example. Okay, so we're going to spend the next kind of 10 minutes looking at a case study that we did for using AutoML for a text classification problem. So a slightly different part of machine learning. called natural language processing. I think it sums it up quite well. NLP is a field of artificial intelligence that aims at understand and generate human, i.e. natural language. Now, there's lots of different subtypes. I'll touch on some of these because they might, spur potential use cases in your organization. But you've got text classification. So, for example, looking at things like sentiment, categorization, i.e., is this spam or not for an email platform? We've got word sequencing, so things like predictive text, chatbots, which my colleague Johannes is going to give you a demo of as well later on. We've got text meaning, so trying to find meaning in text. So the contextual. So if I search for, I don't know, an apple peeler on eBay, for example, I have recently, make sure I'm not searching for an Apple product in that case. I'm actually searching for a real apple, as opposed to an Apple pen, is a product. And then some other ones here: sequence to sequence and dialogue systems. So the one I'm going to dig into here is a text classification problem. So we work with a client who does due diligence, and they had a problem where they had 12,000 documents from a pharmaceutical company in 10 languages, including Chinese. And the challenge there was to identify which documents were pharmaceutical information leaflets. So think about, you open a box of, say, paracetamol, have a little leaflet in it. That's a classification problem. Is it a pharmaceutical information leaflet or not? So this is a text classification problem. Applies to lots of other different applications, so sentiment analysis, topics labeling, spam filtering, intent detection. And really, it's a process of assigning tags or categories to text according to its content. The inputs that you typically have, in our case, it was documents, but you can also have speech. Think about your Alexas at home, written text. There could be messages, web pages, documents, social media posts, could be logs, reviews, voice commands. There's a whole lot of different inputs that you can apply this to. Whoops, apologies. Let's flip back. And then you're basically applying a set of predefined categories to free text, whether it's topics, urgency, sentiment, and in our case, it's class. Is it that leaflet or not? Now, traditionally, you'd approach this with a number of different models. I've listed some here, including neural networks at the bottom there. Now, what we started doing is we used a kind of a traditional approach. So we had one of our data scientists use Python, use the scikit-learn packages, and created an SVM, so a simple vector machine with some TF-IDF processing in it as well. Quite complicated. He's been doing this for a long time. He finds this quite straightforward, but there's quite a steep learning curve if someone who's not really done data science was to try and attempt this. We then had to productionize that. So on Google Cloud, we use a product called Dataflow. So Dataflow, typically we use Dataflow for streaming real time. So we use a pub/sub message bus. So pub/sub is another product in GCP, where you have topics. It's like a subscription model, and then Dataflow is your data pipeline, and then you sync it somewhere. Typically Google Cloud Storage, or BigQuery or Bigtable. So in this example, because we were streaming documents, we were streaming those into Google Cloud Storage. It's fully managed. I won't go too much detail on this, but basically it's fully managed, and it's based on the open source Apache Beam SDK. So once we train that model in Python, I've written the code to do that. We used Google AI Platform to basically allow us to build this ML training pipeline. And the idea was that you could drop these documents into a cloud storage bucket, and that would kick off they would actually go into a cloud pub/sub that would then kick off a Dataflow pipeline that would train the model, and then put the actual ML model itself onto cloud storage. And then the prediction pipeline. So once we had a document or a set of documents we wanted to classify, similarly, we drop those into a different cloud storage bucket that would trigger a cloud pub/sub topic. that would trigger a Dataflow pipeline, and this would use that ML model that we'd trained, and then it would spit out basically, is it a leaflet or not, into BigQuery. And just to give you an idea of scale, how much these potentially could scale, so we had it default workers. So how Dataflow works is you spec up the number of workers that you want. We had the default worker spec, which is fairly low spec, fairly cheap. We had it allowed to scale to up to 10 workers. And the throughput that we got there was 200 predictions a second, which is pretty phenomenal. So it's doing 200 per second and 60 seconds to process their entire cohort of 12,000 documents. And you could scale that, a lot more if you wanted to, or fewer if you wanted to save costs. But yeah, so Dataflow's good product. We prefer DBT because it's simpler, but for some things you couldn't do this in DBT. For example, you wouldn't be able to get this throughput either. So this is, so Dataflow is perfect for that. But this is a really interesting slide. So what we essentially did is so this middle line here, I'm highlighting there, is that SVM model that we trained. So it was trained by Ancoris, one of our data scientists. Data science knowledge is an expert, and you can see the accuracy that model achieved. So 98.77% accuracy, decent precision, decent recall. Took him about a day to build. For someone who'd never done it before, it's going to take you a lot longer. And it took about 76 times to actually train that model. So when we ran that on in the AI platform, it took 76 seconds to train. Now, what we thought would be interesting is to say, okay, well, how would AutoML do if we used that exact same cohort of documents? And let's see how it compares with the expert. And that's why I joke with the team, this kind of man versus machine, can you beat AutoML or not? But I think it's really interesting. So AutoML trained a neural net. It was trained by AutoML. Data science knowledge, none at all. So all we literally had to do is once we had the documents in a cloud storage bucket, we just pointed AutoML at it, and away it went and started training. Now, the training takes quite a long time. We let it run for 6 hours. So it took a bit longer to train, but maybe we just left it running overnight. And then if you look at the results, I mean, they're pretty good. They're not as good as Tom in this case, which is good news for Tom, but they are very good. And they were better than the client. So the client team had used a naive Bayes model, their data science team, and it beat that, right? And they knew what they were doing. They were a good data science team. So yeah, I was personally a bit skeptical of AutoML, but it's actually really, really good. You can see here, and it took 10 minutes to actually build it. Just a bit longer to train. Then if you're thinking, actually, well, surely this thing's really expensive. Well, it costs $18 to train that model. So that's crazy, right? $18. You could barely buy. You couldn't even buy a data science book for $18. So yeah, pretty cool. Okay, and then we'll just touch on. So we talked about, I guess, from the ease of use, AutoML is super easy. BigQuery still, you need some kind of technical capability. You need to be able to write SQL, but you don't necessarily need to be a data scientist. So it's still really good from that standpoint. There are, however, certain use cases where you're going to need essentially more complex AI models, and this is where we typically use things like TensorFlow. So TensorFlow, I think a good analogy with TensorFlow is if you think of it as like an F1 car, Formula One car. So if you know what you're doing, if you're Lewis Hamilton, you can get a really good lap time, say around Monza. But if I was to sit in that car, there's a good chance that I'm not going to be able to even get around in the first corner. And that's really what TensorFlow is. So it's very, very powerful, but it's also very, very complicated. It's quite difficult. There's a lot of parameter tuning that you have to do that feels sometimes quite trial and error. That's why AutoML is a good use case, because it's spending those 6 hours, basically tuning it for you. But sometimes we need to use TensorFlow. Now, if you do use it, so Vertex AI, which is formerly AI platform on GCP, enables you to basically have a fully managed, whether it's TensorFlow, Sklearn, PyTorch platform. You can scale it to lots of different CPUs, GPUs or TPUs, depending on what your budget is. Do lots of cool things like hyperparameter tuning. So I guess as a team, I'd advocate this if you're interested. There's a website called Kaggle. It's actually owned by Google. And it's all around, they'll pitch a data science problem, and they invite data scientists around the world to try and make a model. And then the winning model in terms of accuracy actually often wins a prize, like a monetary prize. So over Christmas time, we actually, as a team, we entered one of these. And it was an image classification problem around a cassava plant, which is a potato-like plant that grows in Africa. It's one of the main crops that's grown in Africa. And it was all around, they had a massive cohort of pictures. So here's the cassava plant on the right. And they had 5 buckets, I think it was from memory. They had healthy. So this example here is a healthy leaf. And then they had 4 other diseases. So we've got this mosaic disease here, brown streak disease. And the challenge was there was a load of labeled images. You had to train a neural net, and then they would fire, I don't know, say 10,000 images it's never seen before and see how accurate your model was. And a really difficult problem, because if you look at some of these plants, I mean, that's a healthy plant, but if I was to look at that, that's very difficult to distinguish, say, between that one. It's actually the disease one. I mean, I think that one looks healthier than that one. But yeah, it was very, very difficult, but amazing how accurate the models were. And this is just an example of what I guess it looks like when you're using things like TensorFlow. So here we are. So you have to set up the TPUs. There's quite a lot of kind of coding basically and configuration in doing all of this stuff. Yeah. So I just wanted to bring that out as an example, but yeah, it's not for the faint-hearted, is what I would say. If you do want to learn it, though, I would definitely recommend doing one of these Kaggle competitions, because a lot of the people they make their models public, so you can learn off these people. I mean, we found it really invaluable invaluable. Sorry, as a team. So really good. All right, and that kind of brings us to the end of this session. I hope you got something out of that. And as I say, the next session next week, the last one of the 3, will be looking everything around how to surface these insights and actually trigger action and get value. We look forward to hopefully seeing you in the final session. Yeah, you can stream the first one if you missed it. And yeah, enjoy the rest of your Friday. And if you're in the UK, I suggest you get your brolly, because it's going to be a wet one. So thank you.